today we're going to be discussing heat capacity and doing some calculations with the heat capacity of water. Heat capacity depends on two factors for a material. It depends on the chemical makeup that material has and the size of the sample. And the way this is actually defined is the amount of heat needed to change the temperature of a substance. We're going to deal more with something called specific heat capacity, which I'll talk about in a minute. Just an interesting side note, when we talk about heat here in America, we often use the term calories. So you've heard that in terms of food. When we talk about food calories, those are actually 1,000, what we would call chemistry calories, if you will. So, it's kind of interesting to think about the fact that a 230 calorie serving of ice cream is actually 230,000 chemistry calories. So kind of a little interesting way that the food industry kind of hides the heat capacity that some of the food that we are eating has in it. Substances with high heat capacities are very good at storing heat. They tend to feel warmer, and they require a long time to heat up. This is true of water. Substances with lower heat capacities are very poor at storing heat. They tend to feel colder and require shorter times to heat up. Metals tend to have very low heat capacity. So if there's something metal near you and you reach out and touch it, you're going to notice it feels cold. In addition to feeling cold, you're also going to notice if you hold that metal for a minute, it'll heat up really quickly. This comes into play when you're cooking. If you have like a metal-handled pot, those handles get really hot very quickly as the heat travels very easily through the metal. We're going to use specific heat capacity, which is the amount of heat needed to raise 1 gram of a substance 1 degree Celsius or 1 degree Kelvin. Keep in mind that changing temperature by 1 degree in either of these units is an equivalent amount of energy. So whether we're talking about joules per gram degree Celsius or joules per gram degree Kelvin, the math isn't any different. There's no conversion that needs to be done. I've given you some examples of some specific heat capacities for some common substances. Water has a very high specific heat capacity of 4.18 joules per gram Kelvin or joules per gram degree Celsius. What that actually tells me is in order to change the temperature of a sample of water, each gram to go up 1 degree has to go up or has to have 4.18 joules of heat energy added to it. Based on this, we can make a couple of inferences about some different materials. So if I had a piece of each of these materials that all had the same mass, so I had 1 gram of each material on the chart, and I applied an equal amount of heat, 1,000 joules, to each one of those, which one would end up with the highest temperature? The one that would end up with the highest temperature would be the mercury, because it has the lowest heat capacity, so it heats the fastest. It would also cool down the fastest. Water would end up with the lowest temperature. However, water would actually hold that heat a little bit better and release it more slowly over time. They say easy come, easy go. I guess that kind of works with this. This has to do with our weather. In central New York, we have a lot of climate protection from the Great Lakes and the Finger Lakes because those lakes hold a lot of heat in. So economically, this is really important for agriculture. It's also really important if you think about the whole wine industry here in New York State. We would not be able to grow grapes the way we do if those grapes weren't planted near the Finger Lakes. The Finger Lakes store up heat all summer and slowly release that heat as the winter months grow a little bit colder, and that slow release of heat buffers the temperature and protects those crops. So there are some calculations we're going to do with this. If you look at table T on your reference table, you have the formula Q equals MC delta T. A lot of people like to refer to this as MCAT. Q still means heat. That will still come out in joules. M still means mass. It'll still be in grams. C is what we call our specific heat capacity. is a constant for various materials. For water, this is listed on table B. The units for specific heat capacity are joules per gram Kelvin. Sometimes you might see a Celsius there instead. Again, it makes absolutely no difference, no converting, anything like that. And our delta T, finally, delta, remember, means change in. So this is a change in temperature, and that will be in Kelvin as well, unless you happen to be using Celsius, and then that's in Celsius. But again, because it's a change in, the amount of change is still the same. And note that this is the only of these three formulas where you actually plug any sort of a temperature into the equation. So we have a sample of water being heated from 283 to 288 K by the addition of 125 joules of heat. What is the mass of the sample? So I know that I'm going to have a change in temperature of 288 minus, 283 or 5 Kelvin. I have a Q value of 125 joules. I do know one other thing. Thinking about what formula I'm going to use tells me that I'm going to need my specific heat value, or my C. That's on table B on the front, which is 4.18 joules per gram Kelvin. What allows me to know that I'm going to be using C is the fact that I have a temperature change. They're telling me it's a liquid water being heated. I don't have any sort of a phase change going on. My unknown is mass, and that should come out in grams. So Q equals mc delta T is our formula. Remember, delta T is really one variable. Some people think they need to plug two things in there, but you don't. So Q is 125 joules. M is my unknown. C is 4.18 joules per gram Kelvin. And my delta T is 5 Kelvin. So mathematically, what you're going to be doing here is 4.18 times 5. And then we're going to do 125 divided by that. Should give you 5.98 grams. What is the amount of heat required to raise the temperature? That's really important because that helps us know it's an MC delta T equation. Of 65 grams of water from 298 to 313 K. So this time they're giving me a mass of 65 grams. My change in temperature, 313 minus 298 is 15 K. And because I know I'm changing temperature, I know I'm going to be using C, which is 4.18 joules per gram Kelvin. My unknown this time is going to be Q, which will come out in joules. Again, I'm using Q equals mc delta T. So 65 grams times 4.18 joules per gram Kelvin times 15K. So we just have to multiply through. Should get a pretty large number. Remember, joules are a very small amount of energy, so it's okay to get a large number for this. 4,075.5 joules. Kind of went a little crazy with my sig figs. I think in reality, this should just be 4,080 joules approximately. Sorry about that. So you have some problems for your homework, and that is it for this video.